Today we might be a bit longer because there is a lot that we need to cover, because basically there was a choice of either postponing the next lecture for somewhere in 2 or 3 weeks, which would be then the last lecture, or just squeeze them both together, and it seems like it's not way too much. It's just a little bit more than a normal lecture. So we're going to do one lecture, and this is the last lecture then that we will have in this semester about C++. Then you're going to have some time to finish the homeworks, to familiarize yourself a bit with OpenCV, and then we're moving towards the project, and the next lecture will be done by Cyril, so not me. Okay. Right. So today we're gonna cover a bunch of topics that we didn't cover before, and that are not really very important for the course until here. So OpenCV will be important. I will try to kind of skim through the first part. I tried to put on the slides all the information you need, so we won't really go deep into examples unless we have some time after the lecture and we can just try them out. But most of those topics are either relatively simple, so they don't really need too deep of learning them, or they are not really relevant for this course, so you will not be expected to be using them during the course. All right, so that is until OpenCV, so we're going to go a bit deeper with OpenCV, and you're going to have an example project that will work with OpenCV, so you don't have to implement everything on your own. You can start with something and then kind of build up on that. Good. So generic programming is it's a huge topic in C++, but we're not going to be covering it here fully. Also because I cannot probably cover it fully, because I don't think anybody in the world knows it completely. There is like a lot of things that are complex and need to know a lot of different quirks of C++, so we're not going to go deep into that, but the basics of it I will try to explain you here. So the idea, like, you can think about it as it's a programming that will generate code for you at compile time. So you don't write code, the compiler generates code for you. The way to do it is, the way to think about it is, so the reason why it was done is to separate the algorithms from the data structures that they work on. So to have some abstraction over any data structure that you work with, and then work with that abstraction instead of the actual type. You can think about kind of the generic class as, for instance, if we would have a class cup, and it can hold anything, right? It can hold whatever, coffee, tea, or beer, whatever you want, right? Like it can be really anything, and that is the idea. So that are the classes that we will want to implement if we are using generic programming. We want to make them work with any data in the same way. So it's kind of related to what we covered with using interfaces and so on, but it's using a different mechanism for achieving that. A lot of techniques that we've discussed, like strategy, interface, and so on, can also be implemented in the terms of generic programming. The errors will be worse, the runtime will be better, so it's always a trade-off. But in this course, we won't go too deep into that. But the idea is kind of on this slide. So there is a keyword template in C++ that you can use for declaring something to be templated, to be generic. So the idea is something like that. If I have a function, which I somehow named wrongly, but it doesn't matter, here, so the idea is that before like a typical function declaration, if you ignore the T and S types over there, so actually you can think about it like this. So if you ignore the first line, then T and S could have been just any classes that you've implemented, right? So it would be just a typical function that you usually have, and it would just use those classes, right? The idea behind template is that now you don't have to use concrete classes. You can just say, yeah, compiler, trust me, there's going to be some classes that I pass into here, some objects that I pass into here, and they're going to have these types. And the idea is that you say, I expect 2 different types, for example. It can be any arbitrary number of those. can be 1. Usually it's 1. Sometimes it's more. And we say, yeah, so we want to template our function on these two types, the t and s. And now suddenly our function takes any type. So it can be, so if I call my function with integer and double, it will know that t is integer and s is double. If I call it with integer and my own class, it will know that t is integer and s is my own class. And that's kind of the main idea behind template. That's what happens all the time when you use templated functions. There is also a bunch of words here that we didn't see before. So this type name, you can use either type name or class. Both are completely valid, and I will use them interchangeably on these slides. A rule of thumb, kind of how to pick the one that you like, is usually if you expect the class T to be of user-defined type. So if you wrote a type and you expect this type to be there, then you typically write class. If you expect it to be some fundamental type or some standard type, you just write type name. But it's a convention. There is no real difference here. Right. There are some, so the compiler will complain if something is wrong and what can be wrong. So in this case, we want to assign something, for example. So it has to be, well, actually not assign. We need to copy construct something because we create a new variable result of type t and we set it to the value that we pass into it. So t has to be copy constructible. And the compiler will try to do as good as it can with the types that you gave to it. And if something fails, it will tell you. It will tell you in a very, 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 very complicated manner. So the template errors are insanely big. So if you've seen like errors with when you're using like vector and like other types, they are all templated classes, and they give you errors which are a bit less readable than you would expect from a simple class that you would write, for example, right? But it's kind of a trade-off. So you get much worse errors, but you get a really, really fast generic code for that. So it's a trade-off. Right. Also, those classes have to be completely defined by the time you're using this function. So if I have my own class and I just declare it, the compiler will not be able to use it unless I define everything in that class. Okay? Right, so sometimes the compiler will, okay, so in this case, the compiler is smart. If you pass here an integer and you pass here a double, it will understand that it's an integer and it's a double. Like, it will just know it magically. But if there is no input parameter, it cannot find out what you expect it to do from the return type. So it won't be able to guess that, and we have to help the compiler. So we will have to use a bit of a different syntax for those functions and tell the compiler what we expect it to do. So in this case, we have a templated function. It's called the dummy function. It does nothing. It just creates an empty thing of type t and returns it, right? Because the compiler doesn't have any input parameters into that function, it cannot guess the type t. So it won't be able to, like, it will complain with some error, something like, yeah, I can't guess the type or something like that. So we have to help it, and let's say we want an integer, so we say dummy function, then we use these curly brackets, just the same way as you've used them for like vectors and so on. And we say, yeah, we want it to be an integer function over there. And then it will return us an integer. And if we put here double, it will return us a double. So that's kind of the gist of it. Yeah, so the classes are just the same. So before we looked at the template functions, you can also do template classes, or structs for that matter. Again, like structs and classes are exactly the same. Yeah, it looks just like that. You just put template class t or type name t in front of the class, in front of the class name, and suddenly this class becomes a template class, so or like a generic class. The idea is that now throughout this whole class, you can use this type t over here. So now you can, like, if you don't know which type do you want to store in your class, let's say your class works completely fine with double, integer, string, and so on, and you don't know which type it will be using, then you just pass the type t over here, into this class, and you can store any type T here. Again, it could have been also more classes than this one. It could have been also another like class S, class whatever, Q, and so on. And then you could have used all of those. It's just like with the functions that cannot know what type you expect them to have. There is no way to pass the type into the class. So we need to tell the compiler which class do we need to instantiate. So if we need an object, we need to tell what is the type of that object. And the type is some concrete type. So it doesn't work if we don't provide a type. So we say, I want my class to be instantiated with the type integer. And this will create an object of this type. So this now becomes the full type. And this type is different from this type. Even though they have the same name, they have the same class name, they are different types. And that's how we can do it. So kind of, you can just try to run this example and see what works, try to change something, try to instantiate it without a type, see what error it gives you, because it's always nice to see what error is there, because you will see this error whenever you try to do something like that in real code at some point of your career. Right. You can also specialize templates. It's a new word, it's a new concept. The idea is that, let's say, most of your implementations should be exactly the same. So you don't need to specialize it. They will work with any type you throw at them. But let's say there is one type which is particularly weird, and you really want to make sure that that type has a specific implementation. And you want to make sure that this implementation is different from the normal implementation. For that, you use this syntax over here. So you say, yeah, so I know it's a template function, and I will give you all the types that you want to have now. Like, if we're talking to the compiler, which as C++ programmers you usually do. So what you do is you say, yeah, it's a template function, but I will just put an int here. So now, when I use this template, like when I use this template, dummy function int, it will actually use this implementation. While if I use double, it will use the standard implementation with any generic type. If I would use string, it would still use the standard implementation. Again, just run it, put some print, like couts everywhere, and see what is being called, what is not being called, and so on. But this is kind of course, in real code, like when you have like huge classes and you need to work with those huge classes, it's going to get a bit more complicated, but the idea is still this, and it's relatively simple. Right. Okay. So the idea how it all works under the hood, I think it's important to get some kind of intuition behind it, is whenever you create a class which is templated, you don't really declare a class. So the compiler doesn't care about it. It will not generate, like you are not actually doing any, like generating any code that will be put into your libraries or into your binaries. The moment that your code gets put into the binary or a library is when you are trying to use an object of a particular instance of that class. So for example, if I have a templated class with type T, and I create a class of, like I create an object where I instantiate an object of, say, my class integer, right? So I put an integer into the square brackets, and now I've got my object of type my class integer, right? At this point of time, the compiler will generate the code, will just kind of copy-paste all the code that you've written for this template class. It will replace T with integer, and it will just copy-paste it into a new file somewhere. It will be hidden from you, and or just replace it in that file. I don't really know exactly what it does, but it doesn't matter for this particular situation. The idea is that the compiler will generate code for you. And that code will be compiled and then used in your binary. Now, if I create a class of type my class double instead of my class int, or along my class int, Now the compiler will look, okay, so I can use this implementation for integer, but I cannot use this implementation for double, so it takes your class with template and it creates another copy of it with double. So it just copy-pastes the code, replacing t with double, for example. And now you have like all the code for your class for integer, all the code for your class for double. And they're somewhere in, you can think about them as being in some header files somewhere. And that is kind of the idea of it. So whenever you create a templated class, you basically create a family of classes that do exactly the same thing. If you would need to write it, you would need to copy-paste that code in many files, and that is annoying because it's hard to maintain and so on. So that's why it was all created. You are maintaining one consistent code base. This code base will be copied by the compiler over and over again whenever you try to instantiate it. The key here is that the compiler will only generate the code for the class when you try to create a variable of that class. Before you do that, the compiler will not do anything. So it will not generate code that you don't need, because there is potentially infinitely many types. You can create any type you like, any class you like, right? And the compiler just doesn't know which ones you will be using. So it can only, like if you have like in your main function, you create an object of class 1 and class 2, it will know, aha, okay, so now you're using class 1 and class 2, so I need to generate those classes for you. And that's when it does it. It's all very nice, and it's very thoughtful of a compiler to do it for us, but it leads to different problems, which are exactly the reason why this is kind of not really in this course. Because it's a whole, like, I would say it's a very advanced topic to use those, like to use the templates right, and usually they're needed for really, really high performance programming, and usually for very, very generic libraries. So that's why, for instance, STL, the standard library in C++, is written mostly in templates. It doesn't incur any overhead on the runtime, and it's very, very generic. So now you can use your vector with anything. You can use it with integers, with doubles, with strings, with unique pointers, and the vectors don't care, right? So that's the idea. The problems come when you try to use your techniques that you learned before to the template classes, for example. If you try to separate them into header and source, it's a whole madness. It's a whole new world of problems. It all makes sense if you think about it, but it's a different way of thinking about those classes. So, as I told you, the concrete implementations of your classes are instantiated at compile time. And the key word here is compile time. If you remember how the program is being, if you want to compile and run your program, you actually do the compilation, then you do the linking, and then you can run your program, right? Because if you separate your functions into header and source files, you will need to link the implementation to the headers of your program. And that is an issue here because at compile time, we don't do any linking. Linking comes afterwards. And the compiler has to know where is the implementation of your classes when it needs to generate those classes for you. Right? So it's kind of like a chicken-egg problem. Like it needs to generate your classes to make sure the linker can link them, but it needs the linker to link them in order to generate the correct classes. So that's why it becomes complicated and it doesn't work. So if you just try to use your classes in header files and source files, it will fail miserably. It will complain all around, and you're not going to have a fun time. There are three ways of kind of getting rid of this situation or making this situation a bit better. The simplest way by far is to just do a header-only library. Header-only library means that you declare and define everything in a header. So you create your file, like your class in a header file, you declare everything, and then you define it in the same header file. Either in place, or you have a declaration and then the definition, but all in one file. And that is kind of the idea here. This way, you don't need a linker because everything is in the header file. So the moment you include that header file, you get everything from it. You have all the implementation, all the declaration, and so on. That is kind of a very classical and a very simple way of doing that. There is also like a small cheat that you can use. Usually it's nearly the same as the first version over here, but the idea is that you put your declaration into a header file, just as you do as usually. Then you put the implementation into the HPP file. It's a convention. Like a lot of people name them in different ways, but I personally prefer HPP. Different people have different opinions on that, but to me it makes sense. The idea is that then you include this HPP file in the end of your header file, which makes it kind of being one big header file when the compiler tries to compile it, because it will just substitute your include whatever HPP with that HPP file. So now your header file becomes bigger and you just don't see it. So you kind of, instead of writing everything in one header file, you write them in two files and you let the compiler make one file of them. But in the end, you get basically one header file with all the declaration and implementation. So again, it's kind of the header-only way. So you don't need to link anything in this situation, and so on. And the last way is different. It is a bit more complex, and it's not always suitable for the needs, but the idea is that you do it as usually you do with other libraries. You declare class in a header file, you define it in the CPP file, but then in CPP file you tell the compiler which class, like which types are you expecting to use. So say if I'm using my class with integer, I will have to explicitly instantiate say a variable of this class given integer. If I use it with double, or I expect to use it with double, I put it with double, and so on. I will not go deep into the details of this here. Probably it's better. So I link two things here which explain this concept. So they're like, this link is exactly about this concept over here. Again, it's a bit out of the scope of this course, but if you're interested, you can have a read. It's kind of one page, like one screen of text, and then try it out if you are interested in that. The problem with that approach is that now you need to know which types you will be using forever and ever. And if you're developing a library, you really can't do that, because you don't know which types the people will be using your classes with. And so if I just say, yeah, I can use my class with, say, integer and double, and then somebody goes like, yeah, but I have a string, and I think it's going to be useful for your program. You say, yeah, okay. So somebody complains on GitHub, and then you go at night and code, and you say, okay, I will also add string here. So now you have integer, double, and string, and so on. And then somebody comes up, yeah, but I've written my own implementation of string, and I want it to run with the same thing because it conforms to the same interface. And you go like, yeah, okay, I should have just started with a header file only approach, because now it's not scalable. So it's a trade-off, and it's going to take a long time to find out which one is better for a particular situation. I don't really think I can teach it in one course properly. But I wanted it to be on the slide to make sure that we don't leave any big gaps here. Right, so that was kind of mostly, that was a very, very short crash course on template programming. Again, we're not going to be using that, so that's why I'm not going into details. The second thing that I wanted to tell you about today is iterators. We skipped that, and I think you heard that word from me a couple of times during the course. I explicitly wanted to avoid them because, to be honest, it's like in a day-to-day programming, you don't really need to use iterators very often explicitly. Sometimes you use them implicitly, but you don't really need to do that explicitly anymore. Before C++11, that would be a valid option. Now, it's always easy to avoid them without sacrificing anything. It's still an important concept to kind of keep in the back of the head, so we're going to talk about them a bit. You can think about them like whenever you see an iterator, like iterator is just a type. So it's a type that iterates over some container. And there are many different iterators, and they are the abstraction that the standard library uses to work with any containers, with any algorithm, and so on. And you can think about them as about pointers. So whenever you see a variable of type iterator, you can expect it to conform to the same interface as the pointer. So you can dereference it, you can use the arrow, and so on. Again, most algorithms in STL, like in standard library, they use iterators. So when you want to sort your vector, you pass 2 iterators to it, which define a range that needs to be sorted. For example, in some lecture where I explained how to sort a vector or showed how to sort a vector, there was this vector, and you pass vector begin, vector end to it. That is iterators. So begin and end are iterators. Right, so there is a bunch of things that you can do. You can dereference it, you can use the error, as I told you. You can even skip to the next element, usually for the iterators with ++ operator, as usually. But usually you should really stick to range-based loops. So the range-based loops are implemented through iterators in the standard library. So you don't really need to explicitly use iterators anymore. And it's always better to avoid making a mistake by iterating way too far and so on. So they have all the same drawbacks as just using a counter, for example, but they're just more abstract than a counter, and they're used in STL. So it's kind of an important concept, but really I think in this course you can definitely ignore that. Right, so one more thing, one thing that you might really see a lot in any code, and it's kind of, I think there's 90% that you hear about iterators, you hear about this line over here. If I have an object which is of standard, in standard library, for example, it usually has these 2 iterators, the begin iterator and end iterator. The begin iterator points to the start of my, say, vector, for example, or string, and the end points one element after the end. So it's not pointing to anything valid, it's pointing to nothing, but it's there to show me that if I'm iterating from begin to end, when I'm at end, it means that I've iterated everything. And you can use it like this in code. So if let's start from above, there are 2 examples here, just to, examples are always better than just a slide. So I feel like maybe that will give you more intuition. So if I create a vector of double and I put 3 numbers into it, and then I want to iterate them and output everything to the console, that's what I do. I'm using auto here because iterator types are long. You can go to CPP reference and see what is the iterator type and how to use it. Usually I would write vector double, then 4 dots, iterator, and that would be my iterator type over a vector of double. But I'm using auto here just to avoid writing it all out. Before C++11, it was horrible because every time you needed, if you have a type, and let's say it's not a vector, but it's a map that is of some other complicated types, and then it's this long, and then in the end you need to write iterator, and then you need to actually declare an iterator. It was horrible. It doesn't fit in 80 characters line, just one declaration. So now we have auto, we're more happy people overall, and I will be using it here. So what it says here is that I start with the iterator it, and I start at begin of my vector, and then I iterate until my iterator is until my iterator is equal to end. So whenever it's equal to end, I'm stopping my iteration, right? So I'm not going into this loop whenever this does not happen, right? And then I just iterate by 1, so I just jump over every next element. And as I told you, you can think about it a bit as about pointers, so I have to dereference the iterator in order to get the value under the iterator. But that's it. So that's all the syntax that you need for iterators, really, for vectors or for simple types. If you're working with associative types, so like map, unordered map, and so on, you have to make sure that, so actually they store kind of pairs of objects. They store a key and a value. So whenever you have a pair, if you dereference it, you will just have a pair. So you use the first and the second. So for example, if I have a map of integer by string and I create the hello world example of it. So this is how iterator looks without auto. I could have just written auto here. It would be working, but I wanted to make it explicit here. And you can see how much longer that is than just writing auto, right? So usually when you're using iterators, really just use auto. It's much simpler. Yeah, and then there is function find in map that returns you an iterator of some object. So for example, if it finds a key 1 in my map, it will return me an iterator to that element. And that iterator will be this it. And then if I output the first, so it's a pair, the first one is the key, the second one is the value. And if I call the first, it will give me the key. If I call the second, it will give me a value. Again, like you can run it, you will see that it actually works. And if it doesn't find an element, so if I now try to search for key 3, it will actually return me the end iterator. And that's what end iterator is usually used for. It's kind of used as an invalid value. So when I try to search for something, it says, yeah, look, I found it, but it's an end. And it means that it's not there. So if I compare my find 3 to end, I will actually make sure that it's not there. But as I told you, in the case of map, you should really just use count because it's much more readable. So consider if I'm writing find 3 equals end, and this is the shortest way I can write the check for 3 being in my map. And compare it to just writing count 3, right? That would be enough, because if the count is bigger than 1, then the if will actually count 3 would be like 0, right? But it's more readable, at least from my perspective. And yeah, but it's all like, there are iterators, you can use them like that. That's basically it. That's all how you use them. And again, you can pass them in any algorithms that you find in STL. Good, so we're done with iterators. That's really, I think, all you need to know about them, not only for this course, but generally for your life. You might try to actually try them out and see how they work for you, but otherwise there is not really much information more about them. There is another concept in standard library that is called exceptions, and they're needed to make sure that we work correctly with errors. So if there is an error that we can recover from, we can use a standard mechanism of handling errors. There are like a couple of keywords here: the throw, try, and catch. So throw means I can throw an exception. If I'm getting something that is not really working, and I just want to kind of tell somebody else that like something is wrong here, and I'm not going to work with this data, I just say, yeah, I'm throwing an exception over, and somebody can actually catch that exception at some point. So there is in the standard library, there is the class exception. It's in the header exception. So if you include exception, it's going to work. Sorry, std except, that's the include. Yeah, and you can always ask for what is being thrown at you by just asking what. So if I got an exception, I can say print me the error message, and it will print me the error message. Yeah, and this error message can be put into the constructor of the exception class. Again, this slide is very blotted, like there is a lot of text. I usually try to avoid that for the purposes of understanding, but you shouldn't really understand that completely now. We're going to go into examples, but I just wanted to make sure that this is there and you can always refer to it. So there are a lot of different exceptions, and if we are going to use any, we're probably going to use these two. So there is a runtime error and the logic error. So the runtime error is when something is wrong at runtime that you expect it to be correct, and you really don't want to carry on. Like you say, okay, this is so wrong that there is no way my algorithm will work. And you say, yeah, okay, so I will just notify somebody about it. Somebody has to deal with it. I don't care about it anymore. And that's when you throw the runtime error. And you can always specify the message that you actually want to say. So say, I don't know, like my pointer is null and I don't expect to run, for example, right? There is also a logic error that can be kind of undone by the user. So if you just see that, well, okay, like it's definitely a logic error, the user thought about it in a different way, you can throw this exception too. You can also catch exceptions. So for example, if there is a function that throws some exception, for example, this unsafe function, if in this function somebody throws an exception and we expect that, we can actually recover from that by using the try-catch blocks. So we say, let's try to call whatever code is here. So we use try for that. And then we try to call that code. It does its dirty thing and throws the exception. Then we catch those exceptions. And we can have multiple catch blocks, and they will catch their own particular exception. You can think of them kind of a bit as functions. So this will only work for this type, this will only work for this type, this will only work for that type, and so on. And this is actually valid C++ syntax. It just catches everything. Like anything that somebody has thrown, it doesn't care. If you didn't catch it before, it will catch it there. Right. So, and every time we catch it, we actually ask what is being thrown at us. So that's kind of the syntax. And the idea is that you can throw exceptions at any point of time. And if you expect somebody to throw exceptions, you can use try and catch to try to avoid issues. So for example, here, if there would be a logic error, I would try to parse the logic error, find out what's going on, and then try to rerun that function with the correct argument, for example. Yeah?
What do we need to throw for?
The throw, we need to explicitly throw errors. So if you write a function that you want to stop executing, if you, let's say somebody gives you a pointer, for example, and then you need to dereference this pointer at some point of your program. What you can do, you can, before you start your function, you can say, let's check if it's actually null pointer. And you check it for null pointer, and you say, well, no, that's a logic error. I expect it to be not null in my function. So you say, throw logic error, I've got a null pointer, for example, right? And then somebody else might get this exception for you, and it was like, oh, okay, well, I was not expecting that you need it to be not null, so here's another pointer which is not null, and then you can work with it. So that's kind of the idea of it. Yeah. So there is an exception class. It's this is a class. It's std exception. You can try to read it, but it's heavily templated code. It's hard to read.
When you use the catch, you should test for each type of exception.
So that's the thing. You shouldn't really use them, really, I think. Because in this, I mean, there are definitely good cases for using exceptions. It's just that I'm not aware of those. So I don't use exceptions in my code. You kind of try to make sure that if your code can work, make it work. Like if you can't work, then just crash. I mean, it's much better to crash early than to go into a weird loop of trying to recover if you don't really need to recover. So the problem with exceptions is when people start using them, they start using them everywhere. And that is really bad because it propagates everywhere. And then all the code kind of throws all the exceptions for you, and then you need to have like 15 catch blocks because everybody used their own exception thing, and it gets really annoying. So if we stick to the Google style sheet, again, it's not really relevant for us because it was Google's decision to not use them. So in their code base, which is like 100 million lines of code approximately now, they don't use exceptions nearly anywhere because it takes a lot of power and a lot of force to rewrite the code that uses them and to communicate with other code that doesn't use them. So it's not a hard decision here. I can't tell you to use them or not to use them, but I feel like you can definitely survive without using them. You can still you still have to check if your pointer is null, but say, what about just writing an error message and not doing anything, for example, right? So you can always find other ways of kind of getting rid of the same problem without expecting somebody else to catch your exceptions, right? It is still a very important concept that a lot of people use, so I definitely wanted it to be somewhere in the lecture, but the reason we're doing it in the last lecture is because it's not going to be important for this course. I don't expect anybody of you to use exceptions unless you really want to find out how they work in this course, but yeah. You can also read about them. So again, I linked the CPP guide over here, so you can click that when you're at home and read the ideas why Google kind of doesn't use exceptions, what are their pros, what are the cons, and why the decision was made not to use them. Yeah, like I really don't have enough experience to tell you exactly why it's bad or good. I haven't written like millions of lines of code, so I haven't worked with a code base of 100 millions of lines of code. So I trust Google on that, to be honest. Right, and then there is a couple of more topics which are kind of smaller, I think. So we have talked about the main function and those parameters that you pass into it a bit. So I always try to remove them when I show you examples, so these guys over here, because they were never relevant for our code that I was showing you at the lectures, but now they become relevant because you can actually use them for something useful. But it's really very simple. If you understand what a function declaration is or a function definition, then it's just the same. So somewhere hidden from you, you can think about main being declared with two parameters, the argument count, argc, and argument values, argv. So argv is this complicated type because it's inherited from C. If it would be implemented now, it would be an array of strings, for example, or a vector of strings, and you can think about it that way. It's just an array of strings. By default, if you just run your program and you have your main function without these parameters, the default values will be used. And the default values are actually, so argument count is 1, and the argument value is the path to your binary. It will be populated automatically for you. And they will always be there. So this argument, the first argument will always be like that. And it will always be the path to the binary that you are actually running right now. Just to kind of give you a small example that you can actually run, if you run this program, it will output on the console all the parameters that you pass to it, for example. And you can pass anything. So how do you pass those parameters? You just run your, if my program is called main, for example, I would type main 1 space 2 space 3, and it would run this program with those parameters passed into it. So it's as simple as that. And you can kind of iterate over the all argument C until you have as many of those, and you can output this argv. You can also set it to string, just like here. So you can say string program name is argv0, and like that's the way you can work with those. It's useful if you want to pass something into your program. There are more advanced techniques that we will not cover here, where you can actually parse all those arguments, and this way, so if you know all the programs that we've been using in terminal, they usually have some flags. So if you type like ls or like copy, for example, you can type -r. So -r is just another parameter as input to their main function, and they actually parse it and find, hey, is there -r? If there is -r, we use this functionality. If there is no -r, we don't use this functionality. So that's what they do. It's a bit more advanced, but there is nothing new here. It's just another library that somebody has to write. Either you have to write it or somebody has to write it and you just use it. But it's all building up on this very simple concept. There is nothing, it's just number of arguments and then the arguments. And you can use them for anything you want. And they're all strings, so you have to convert them to anything that you want. If they are, if you expect, like, say, an integer, then you can convert it to integer, and then you can actually try to make sure it's an integer and so on. So it's kind of your work. The next thing I didn't cover before, we kind of touched it a bit with using. Using is a very powerful word in C++ 11, and it can be also used for type aliasing. So we can call a type by other name. Usually it's used for making names shorter, especially when people code in this templated programming. You have those names of types. So if you define a class, your class becomes everything along with the explicit types that you pass to it. And sometimes you really don't want that. You want just a short name, but you need to provide all of those words here. So you can kind of mitigate it with this. You can use using new type equals old type, and usually this old type is very, very long, and new type is much shorter, and that's why you're usually using that. So there are kind of, you can think about two ways of working with it. When you're using it outside of functions, it can be used like anywhere in the code. If you're using it outside of functions, it declares a new type, basically. So it says, yeah, so I declare this type, now you can use it, and this type is going to be exactly equal to this type. So, and that makes it useful for you. You can also use it inside of the functions. Then it does exactly the same thing, but it will only work for the scope of that function. So in the end of this function, you will not be able to use this type anymore. It's only there for some short-term simplifications of your syntax, basically. You can also use it with template classes. Again, like this is kind of a relatively complex example if you never worked with templates, but try to not be scared about it. It's not really too complex. So again, feel free to try to run it. The idea here is that let's say we have a struct image and we want to say it can store anything, and we can also provide an integer size. So it's also a template argument, but we say it's going to be an integer. It's not going to be some class. It's going to be an integer for sure. And that what we use is we create an std array of some type and some size, and we know that at compile time. So that's why we can use the array here. Again, I use struct just to save space as usually. The problem now is that now if I want to declare my image, now I have to actually write, yeah, I want my image float, whatever, 3. And it's a long name. I don't want to use that long name. I'd rather have some one word that would explain that. So first of all, I can use using. Using can also be kind of merged with the word template. And in this case, I say, I will template this on the size. And then I say, I will be using image f as image float and then this size. So what it does, it says, I will be using this class with float as the first parameter, for example, and then this will be known from now on as image f. And image f will still be a templated class over here. So now when I actually want to use the image f, I can use it in a function, and I say, well, I'm going to be using my class image3f, for example. And image3f will be just this. So it's image f, passed 3 as the template argument, so it's going to be image3f. And now I can just use it as I want to. And also, like, yeah, one more thing is like this pointer here. I use it, like, again, using can be used everywhere. So I use it also in the class. And I say, I don't want to write std unique pointer image t size all the time. I want to write pointer. That's all I want, right? So what I say is, this class will be using class pointer, and this pointer class will be equal to this. So how can I use it? I can use it like this. Now I can say image3f pointer, and then I just pass new image to it and create a unique pointer of my image. And the syntax is, I hope you can see that this syntax is much better than if I would write image float 3 and all this in std unique pointer and so on. So that's why it's used. It's just to make your code more readable and nicer. There is no really other purpose unless we're going into really complicated templated programming where some concepts are not possible without using it, but we're definitely not going there. Right, so I hope that is a bit clear, so you can use it like anywhere. I tried to put on this slide all the use cases for using that you might encounter in your life, so you can see there's like one in the class, there's one outside of everything with a template, and then there is one more inside of a function. So this one will stop existing by the end of this function. If it wouldn't be main, it would make sense to just use it in this function, for example. Right, cool. So we are done with all the kind of basic stuff that we didn't cover before, and is there for you. So again, this first part of the lecture is just for you to come back if you find the concept somewhere. If somebody uses, say, templates and you see the syntax and you go like, oh, what is that? And we didn't cover that in the course. And then you go like, oh, okay, I will go to that lecture and there is going to be some information about that. So that's why the first part of the lecture was there. The second part is something important that you will be using for further course. So in the project, we're going to be using OpenCV, and you're going to have to use OpenCV too. It is a library, just like we've been using this libpng library for reading images and writing images, for example, right? So this is just another library. It's a huge library, but it's a library. So we will also be searching for it, we will be using its headers, we will link to it, and so on. We're going to be using version 2 of OpenCV. There are 3, so there was like the initial OpenCV, then there was the version 2, then now is the version 3. But because of some issues at how easy it is to install the third version, we are going to probably stay on version 2. That might cause some issues, but we're going to try to solve those. And we are going to be just using a small part of it. So this lecture does not even pretend to tell you everything about OpenCV. It's a huge library. To build it, it takes like half an hour on a PC to just build everything. Maybe not half an hour, but a lot, like very long. Most of the things in this library are in this namespace, CV, and they have a website. So it's insanely popular library because it's under the FreeBSD license, so it can be used for commercial and non-commercial uses without attribution and so on. So that's why even a lot of companies use it until they implement their own version of some algorithms. They just say, yeah, let's just try to use OpenCV for now, and then we're going to re-implement it if we need to. But so it's actually really useful, and it's used a lot in the world. Let's start talking about this library, and we start talking from data types. I feel like it's very important because OpenCV is written, so it uses their own data types. And by data types here, I mean that they have some enum or some number of integers that define what types are going to be used. And it's going to be clear, hopefully, in the next couple of slides, what I mean by it. The idea is that OpenCV tries to be very fast. So it tries to not stand in your way. It just tries to make sure that if you tell it to do something, it does it. The problem with that approach is that it actually relies on you to know what you're doing. And it's a big issue because sometimes you don't. And if you tell it to do something wrong, it will not correct you. It will just do it. And then you will see a wrong result, and you will be sitting and like, okay, how did this happen? Like, why do I see this and not what I expected to see? So that's why thinking about types in OpenCV is important, but we're going to try to develop a couple of techniques that can help us with that. Okay, so every name of a type in OpenCV is called like this. So it starts with the CV underscore, then the number of bits in this type, then some identifier, and then the number of channels. So for example, there would be, you can have an RGB image which is CV underscore 8-bit unsigned char 3 channels. So it's a color image where every channel is completely filled with unsigned characters, and unsigned characters are all 8 bits, so 1 byte. So every char is 1 byte, so that you will need to remember here. For grayscale image, for just like black and white image, you usually use CV8UC1. It's a bit cryptic from the start, but with time you get used to those types. So actually what it tells you, it's 8 bits, unsigned char, and it's 1 channel over here. So that gives you a black and white image. And why is black and white 1 and the color is 3? It's because black and white just needs like intensity basically, and in RGB image you need 3 channels of intensity for red, green, and blue, right? So I hope that makes sense. Again, we kind of did approximately this when we were writing our own class image with this pixel thing, right? So it's kind of the same. That's why I wanted you to implement that, because now you won't need to have your own like image class and so on. But the way it's implemented, it's kind of like what you did, just a little bit more complex, a little bit more complete. It's hard to remember those types, and usually you just want to make sure that you just want to use some type, the real C++ type, instead of that. So for example, you can type something like this. You can say data type, unsigned integer type, and it will actually give you this. So it maps from a type to some integer that you can use instead of any of those. I recommend you using this because you will need to remember the type that you're using in order to get an element out. We're going to talk about it in a bit. Okay, so there is a basic matrix type. So the matrix type is what you did for an image, for example. This is done here as CVMat. So CVMat stands for matrix, and it's a general matrix type. You can use it for all the matrix operations that you're used to. You can multiply them and so on, but you can also store them as images, read them from images, and so on. There are 2 versions of it, and one is more classical one. The other was added later, as far as I'm concerned. And the classical one was just you create a CVMat, you call it an image, then you call it constructor. And its constructor, again, is just some class. So everything in C++ that is not fundamental type is just some class. So somebody has implemented a complicated class CVMat, and that's what we're using. So the constructor of this type is, it takes the rows, it takes the columns, it takes the data type, which is that thing from the previous slide, this identifier, whatever, CV8UC1 and so on. And then it takes some value if you want to fill it with some value, right? So it's fairly similar to how we used like a vector or something like that, but now it takes the rows, columns, just like your image class did. And the only difference is that this data type that they require you to know in order to make sure that the matrix is filled correctly. Another way of doing that is to actually use, so they also have this mat_t, and it's a templated type. It's built on top of this one, and then it tries to use the correct data type for you. The idea here is that you create a mat and you pass here, for instance, unsigned integer, and then it's going to be an unsigned integer image, and it will figure out on its own that it has to put the CV8UC1 there. I personally like this one because I like being sure that my types are correct, because making a mistake in types is painful here, but you can use any that you like, and the examples will cover both of them. Right, so again, like there's going to be a bunch of using here. So for example, I can create a CV image with Also, it's nice to initialize it with zeros. It's a good idea because, again, if you just create it without passing any value over here, it's not going to be initialized. It's just going to say, okay, now this memory is mine, and I don't care what there is. Like I expect somebody to put something into that memory. But if you say zeros, it's going to say, okay, this memory is mine, and now I'm going to just fill it with zeros, and that's it. So zeros is always nice because you at least know that the values that you didn't touch will be 0 and not some arbitrary garbage. Good. So what you can do is you can either create an image like this with CV mat zeros, and then you have to also provide the type. So it will also fill the multi-dimensional images if you want to. So if you have like RGB image, if you pass this over here, it will fill like 10 by 10 3 times, all with zeros, right? So it does what you expect here. I still feel like the syntax for the explicit type is better. So if I want a float image, I can use matf to make sure I'm using float. And you can use zeros from here. So if I wouldn't use using, I would have to write this thing over here and then put the 4 dots and zeros. So this syntax is a bit more complex, but if you're using, it becomes simpler and you are more protected from using the wrong type here. So here I don't have to specify this over here because it knows its type already. And this will create me a matrix that will be filled with floats, and it's going to be all zeros, right? There is a bunch of functions of that class that we can use. We can use the type to get kind of this number from an already existing image. It's useful if you expect your image to be of some type in your function. You can, before running your algorithm, you can actually check if your type is correct. And in documentation, you can find all the integers that correspond to those types, because every of those is just an integer. You can print it, and it's going to be like 2, 8, or something like that. I don't remember them from the top of my head. Maybe I will even put a slide on that afterwards, but they are in documentation of OpenCV. You can look it up. You can also get the size of an image by 2 member variables. They're like rows and cols. They are not a function, which is weird to me, but I think it's for historical reasons. So you don't need the parentheses here. It's just you ask for rows and you ask for columns. I don't know what happens, though, if you try to change that. So I never tried that, and you shouldn't either, because it's kind of asking for trouble. So maybe you can, but you really shouldn't. You can read an image, you can write an image, you can show an image on the screen. These are the 3 kind of I/O things that you can do with OpenCV. To read an image, you can use imread. To write an image, you can use imwrite. To show an image on the screen, you can use imshow. And when you're reading or writing an image, the extension will be respected. So if you want to write a PNG file, you just write, I want to write my image.png, and it will know to use the PNG writer. So just the way we did, but now it will kind of have an if statement, and it will say, yeah, okay, you're using PNG, I will use the PNG strategy. If you're using JPEG, I will use the JPEG strategy. And there is a bunch of formats that it can write and read to and from. We're going to cover that now. But the idea is that it will know about the extension. I don't know why my slides are a bit cut off, but hopefully it won't cut off any important information today. Okay, so another thing that is very important to remember about images is we were talking about smart pointers, and CVMat is like, so CVMat is a huge class. It does so much. It has a lot of functionality. And apart from other things, it's a shared pointer. So it doesn't copy your data when you copy a CVMat image. And again, it was done for you to make sure that you're not doing something that costs a lot of time, because copying like a huge image would cost you a lot of time. So that's why they decided to implement that. And a small example for you to try out and to make sure that you understand what's going on is something like this. So let's say, again, I create a float image, I fill it with zeros, and then I try to create a copy. I even called it that it's not going to be a copy, just to make sure. And I just kind of try to create, like, use a copy constructor for it. The problem is that if I wouldn't know that CVMat is a shared pointer, I would expect a copy to be actually instantiated, but it doesn't. So if I now try to change, so you can use the function at, you need to pass the type over here, and then you, let's say I want to set the fifth pixel of my new image of my copy to whatever, 42, 42, I don't care. And then I try to output the original image. So if you run this program, you will see that it changes the original value in the original image. Because they are pointing to the same thing, they're just being reference counted, and it's just a shared pointer. It's not implemented in using the shared pointer because it was implemented before shared pointer appeared in C++11, but it uses exactly the same concept. And the idea is that you just need to remember that when you just try to copy an image, it will not copy, it will just share a reference with somebody else. If you want to copy an image, you use clone. So you use image.clone, and it will actually create a complete copy of your image, and it will pass it to somebody else. Yeah, that's all you need to remember. If you want to run this example, it's going to be a bit harder for running it, because now you need to have all the libraries and all the headers. And for that, the simplest way would be usually to create a small CMake project, which you all should be now experts in, I hope. So if you don't want to do that for running a simple example, you can just run this line over here. So if you save this as a copy.cpp, you can run it like this. So what it does, it compiles it, and the new thing that we haven't seen before is this line over here. It uses the backticks. The backticks in terminal say, run it and give me whatever the result of it, like here. So what it will do, it will run this and then replace this line with the result of this command, of this small command in the backticks. And this command just gives me all the libraries and all the include folders of anything, of any library that I have. And I have OpenCV library, so it will go there and it will find all the libraries and all the headers for that. And it will pass them here, so now I can actually run my code and link it against it. You can always just run this without anything and see what it outputs to kind of get a feeling of what it outputs. Try to understand what it does. So don't just, I mean, if you just copy it to your terminal and run it, it's gonna work. But try to understand what it does instead of just running. Again, you won't, like, it's just for easily running the examples on the slides. You're not going to be using that so I don't expect you to use it in your projects. In the projects, it must be a CMake project, because otherwise it's going to be a hell of maintaining all those scripts. Good, so let's talk about imread a bit. It's just a function. It's declared like this. It returns you a CVMat. You give it a file name, and you give it a mode. So what is a mode? A mode, there are 3 modes that I know of. Again, they are changing now in OpenCV 3, but in OpenCV 2, there are 3 of them. And they're called like this. It's just some integer. So it's a CV load image unchanged, which is any integer below 0. There is CV load image grayscale, which is 0. And there is any integer bigger than 0, CV load image color. So it will try to load a color image in this case, a grayscale image in this case, and it will try to load the image in the way you stored it in the first case. Yeah, so that's the way you use imread. So there is again a small example. If you have, like, you can create one image like this. So for example, I want to load the OpenCV logo or any other image that I want, and I say, well, it's a PNG image, so it will just load a PNG image for me. And I'd say, I don't want it in color, I want it in grayscale. So I say, yeah, load it as grayscale, please. And so it will load it, and it will actually create the CV mat with some type. And that is where most of the errors come in. Whenever you read an image and you don't know what type it got, it's going to be an issue, because if you then use like at some pixel, and you pass the wrong type to it, it's not going to be a fun life. The better way from my perspective is to actually expect some type. So let's say I will create my mat of unsigned integer 8 bits. So it's basically unsigned integer 8 bits is an unsigned char. It's 1 byte unsigned char, which is exactly what I expect it to create over here, but now I've written it explicitly, because now I understand what is going on, and I expect the OpenCV to do it for me. If it doesn't do it, I expect it to fail. Yeah, and then I do the same thing. And just to make you convinced that it actually works, I also output here that the type of one is equal to the type of another, so that I'm actually doing what, so it's actually doing what I expect it to do. Yeah, so that's basically how you use imread. You can use, like, you can read color images, grayscale images, and so on. Imwrite is exactly the opposite. If you already have a mat stored in memory, you can write it to a disk or to the hard drive. Again, the format is guessed from extension, and the function is declared like this. It returns you a bool, and you can use imwrite, you pass a file name, and you pass the actual image to it. And yeah, so to use those imread and imwrite functions, you can use this header. So it's in OpenCV2, hi-GUI.hpp. Again, HPP, HCC, I don't know. A lot of people can call their files in different ways. It doesn't matter as soon as they do the same, as soon as they serve the same purpose. The C++ doesn't care how they're called. It will just copy that file over. So OpenCV tends to call them HPP because they have implementation sometimes in the header file already. Right, so what you can do is you can, like, let's say I read this image as a color image, and then I just write a copy of it as JPEG. That's a very simple program. It doesn't do much more than that. And you can see that it's very simple. So I just write an image, I read an image, and then I write the same image out. That's basically it. That's how you use imwrite. So it's a very simple function. There were issues in the previous courses of this, so in previous years of this course, when people try to create a float image or like float mat, because it's just a matrix, and sometimes you want to store a lot of float values there. And if you want to store a lot of float values there, you might be tempted to actually write them to disk in some way, and then to read them, to store them, and then to read them from disk. The problem with in that is that OpenCV hides a lot of functionality from you. And OpenCV expects, if you're using a float for your type, it expects you to have your values from 0 to 1. So it expects that 0 is black and 1 is white. And if you violate that assumption, it might do weird things. It might cut off some precision. I don't really know exactly, so I can't predict what will happen to your files if they're not in 0, 1, if they're float and you're writing them to, say, PNG file. The solution to that is to save them not as image, but as some other file, which also is supported by OpenCV. So you can just store them to the EXR files. It's some open format to store data, and OpenCV supports it. And you can store any floating points numbers in those EXR files using imwrite, and then you can load it with imread. Just make sure you're using the unchanged specifier. Right, so like a small example how to do that is again on the slides. So I hope you will make use of it. And I urge you to take this example and try to replace the test EXR with test PNG, and just run it again and see that how does it work? Or does it work? Does it not work? What is going to be the value after storing and reading it? And so on, right? So in this case, what I do is I create an image, I set some value to it, I write it to some file, which is test.exr, and then I read it from the same file, so from this f over here. And then I just check if the value is still the same, right? So this program is very simple just to make sure that we understand what's going on when we write and read from disk. So feel free to try it out with, say, PNG and JPEG files and see what changes in your value that you're storing there. Again, try to not store things in JPEG because JPEG is a lossy format. It will compress your data. So when you read it, you will read slightly different data than you stored. Use PNG, like PNG for images, EXR for values that are not images. Okay? There is another useful function if you don't want to store things to disk and you just want to show them. There is an imshow function. It might lead to weird errors because it actually runs in another thread and it creates a GUI for you, which you don't have to really care about. So you kind of have to be a bit careful with it, but usually it works just fine. So maybe in like 0.001% of the cases when you run it, something might be off. Not when you run it, but when you implement it, something might be off, but usually you're going to be fine. The idea is that you create an image, you create a window for it, and you give it a name, say window name, very original name, and then you use the CV named window to create this window, and then you use imshow in the window this image, right? And if you use the wait key function, it will wait and not die instantly. So if you don't use this wait key function, it will just continue on running your program and it will end your program, so it will kill everything and you won't even be able to see your image because it will create a window and then instantly close it. So you won't see the image here. But if you use the wait key, it will wait for the user to press something. And then you can see the image, and when you press it, it will close the program. Again, like I don't want to go into details of how it is implemented. It's not really relevant. It's just a tool that is very useful to use here. Another thing that I want to talk about is the OpenCV vector type. So we've seen how to store a value with when the type is float or unsigned char and so on. But if I have a type that has multiple channels, how do I get a pixel, for example? How do I get a value of a single pixel that will be like 3 values, so like RGB, for example? And for that, it's a templated type, so just like, for instance, vector in standard library, and it's templated on type and size. And it's called CVVec. You generally really never use this version of it because there's a lot of type defs. So like type defs is aliases, just like what we saw with using. What they do here is they say, well, vector 3f is going to be vector with float and 3. The vector 3b is going to be vector with unsigned char and 3, and so on. So they define a lot of those types already for you so that you can use them in a short way. How to use them, it's just as you would use the other types, but now you're using vector instead of, say, float, for example. So if I create a mat and I pass the 3-channel, I expect a 3-channel image with unsigned char, then when I want to get a value of it, I can get a value like this. So it's a vector 3b. I don't know what forced them to call vector 3b, but here unsigned char. I don't know why they couldn't write vector 3uc or something like that, because it's kind of confusing. But the idea is that unsigned char takes 1 byte, and that is why vector 3b, b stands for byte, so it's 1 byte. Again, it might be a bit confusing, but I hope you're going to get used to that. If unsure, you can always just define your own type def for this class, and then you're going to be fine again. The same works for vector. You can declare the matrix of vector of 3 floats, for example, and then you're going to have a kind of a color image of 3 layers of floats, more or less. And you can also use at with that with vector 3f, and if you run it, it will output you zeros in both cases. And again, so this type vector, it has so the cout operator, this operator is overridden for it, so you can just output the whole vector. You don't have to output any particular element of it. So if I just write it like this, it will output me 3 zeros in brackets. Good. I wanted to have this slide very explicit. You really, really, really have to think about the types in OpenCV that you're using, because mixing them up is very painful. Like throughout the years, I've been burned by this many times. I've seen a lot of students being really, really enjoying coding in C++ and OpenCV because they mixed up the types. So please make sure that you understand the types before doing something, because the errors, like there won't be errors, it will just do stuff that you don't expect it to do, and you will see weird artifacts on your images, for example. The idea is that you can think of OpenCV not doing anything else apart from reinterpret cast. So when you're doing the at, if you say, I want something at this pixel and I expect float to be there, it will say, okay, you know what you're doing. If you want a float, I will give you a float. If there are actually not a float, but say 3 bytes of this pixel and then 1 byte of the next pixel, it won't care. It will just interpret them as a float, and if you set a value to it, it will set instead those 3 bytes. But then when you show it or print it or put it to the like if you write it to disk, then it will still interpret that as bytes. So it will be an issue that you will see when you write an image. And usually you see like stripes over the whole image and so on. Maybe I can even show you an example now. Like, let's see if the timing works out well. Then I will show you how it looks like in real life. Yeah, so make sure you're using correct types. And by correct, I mean consistent. So if you declare an image with a type, make sure you're using this type when you're accessing its pixels and so on. And that's why it's nice to use explicit type when you declare an image, even when you're using imread, because then you're at least sure that you're using the same type. Right, so this guy tells you that something is going to go wrong, and this is exactly the example that I wanted to give you. You can always just run it yourself and see how it looks like. I'm not sure it's going to be really seen well on the screen here, but we can always just try to do it. So the idea here is that I create an image of zeros, 800 by 600, and it's an unsigned char image. So I can show it to you, then there is a wait key, so it will show me a nice image from the start. It's going to be black, probably. But then what I do is, now I want to go over the whole image and set all the pixels to 1. And somehow I thought that it's going to be a float image. I don't know why. So I'm using float here. But the problem now is that here I'm loading it as unsigned char 3 channels. And here I'm using float. So I expect it to be 1 channel float image. And the OpenCV will not correct me. It will not say, well, everything is fine. I will just do whatever you ask me. So feel free to use any type that you want. So I will set everything to 1, and then I will try to show it again. So let's see if I can run this example. Slides, listings, OpenCV. Okay. So that one should be, how did I, probably bad types. Okay, so this is exactly the command that I was showing you before. It's a bit, whoa, it's not fitting to the screen. Sorry for that, come on. This projector doesn't show the sides of the screen, so I will try to avoid that error. Okay, cool. So now you can see that I just compile this bettypes.cpp, and I just provide all the libraries and so on to it. So let me just try to compile this. Now it has compiled to the A out, and if I run it, this is my window. It's not very interesting, it's just black. So it's not that you don't see something, it's actually black. And if I press the key, now you don't see something. Okay, you will have to run this example on your own because there is kind of like a small, can I zoom in? No, I can't zoom in. Okay, yeah, you will have to run it on your own because it's kind of like, there is a stripy pattern on that image when you rerun it, because it just tries to write the floats everywhere, even though those are not floats. So one float comes for 3 or for 4 of those unsigned chars. So it writes it to RGB of that pixel, and then to the R channel of the next pixel. And that's what it does when you write one float instead, right? So it's just remember, it's painful. Don't mix up types. Okay, so now that we've kind of covered the OpenCV at this point, the things that you will be using, you will not be really using much more of kind of those were the basics of OpenCV. We're going to cover like 2 more classes that you will be using here, and we start. So I hope probably most of you have heard about SIFT descriptor at some point. It's covered in many other courses that we offer, but the idea here is that you want a point in an image to be described by a vector of floating point numbers, for example, and you want it to be described in a way that if a camera changes angle a bit, or if the illumination changes, or if something else changes slightly, then this point would still be described by nearly the same float, like vector of floats. How is it done? It's done like this. So let's say I want to describe like a point somewhere here. Then I cover, and like these are all pixels. Then I compute the image gradients by computing the derivative over image in the x direction and in the y direction. And I now know the directions of all the gradients, and then I summarize them into the histograms of those gradients. Again, like this is not really the course about SIFT. If you want to read about it, I will link, I will put a link up for you to read about that. Also, it was covered in other lectures that there are also recordings about. So if you go to our YouTube channel, you can find the SIFT explanation easily. But the idea is that you describe a point with a vector, and this vector is just all those histograms summarized into one vector. So that's what you will need to do eventually. There is also a paper about that was originally done by David E. Lova, and that's a very, very well-known paper. So SIFT is one of the most used descriptors, or was one of the most used descriptors until recently. Now there are better descriptors that are trained with deep neural nets, but they work much slower, so it's still a very, very, very valid concept. And we're going to be using that in our course. So if you want to extract SIFTs with OpenCV, you can do that. You can, there is a SIFT feature detector, a class in OpenCV, and you need to detect the key points. The key points are just the points of interest. They are basically when there are corners in the image and so on. So whenever you have those, you can detect those as points of interest, and then you can draw them on an image, and you can extract from the key points, you can extract descriptors with the SIFT descriptor extractor. I will probably not, so this is kind of the way you do it, but it will be provided to you as a small project. Actually, I think you already should have gotten the email that you've been granted access to a repository on our Git. There is a CMake project that does all of those things so that you can just run them and see how they work instead of trying to figure out how they work on your own. But basically, you need these two classes in order to work with sifts. Another library that we might be using in this course, it's not mandatory, but it's very, very useful to use. It's called FLAN, and it stands for Fast Library for Approximate Nearest Neighbors. And the idea is that if you have a bunch of vectors, and they're just randomly, so think of them as points in some space. Then you take a point, and now you want to find the closest point in that space, given all of them. The simplest way would be to just go over all of them, compute the distances to your point, and so on. But it's very slow, because now you have to compute the distances from every point to all other points. And now you've maybe found the nearest neighbor for this point, which is, so you always have to go through all of your data. And your data, you can have a lot of them. You can have a lot of multi-dimensional vectors, like 50-dimensional vectors, and a lot is like a couple of like hundreds of thousands of them. And it takes time. So the better way to do it is to build a KD tree. It's a data structure that allows you to query for neighbors quickly. So you build up this KD tree, and then you can query for neighbors in logarithmic time, which is much, 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 much faster. If you want to find out how much faster, you just take a number, say, I don't know, 100,000, and then just put it through the log function, and then you'll see how much nicer everything gets. So the way to use it is you build up again, it's all part of OpenCV, so FLAN is distributed as part of OpenCV, and we're going to be using it from OpenCV. And it's in the namespace FLAN. So what you do is you create some index parameters. You can leave it empty. You don't need to specify any parameters. The defaults are fine. And then you create a KD tree with some data, which is just a bunch of vectors or a CV mat, for example, and some index parameters that you pass from here. And then you want to, say, find the nearest vector index out of your data and the nearest distance. So what you do is you create a mat of nearest vector indices. Let's say it's going to be 1 by k, which is also 1, so it's going to be 1 by 1. It's like a very stupid matrix of 1 by 1 in this case, and it's going to be of integer type. This is going to be of float type because it's a distance. And then you can do the KD, on the KD tree, you can do the KNN search with a query of what vector you are trying to search for neighbors of. And this will return you the index of the closest vector from your data, and this will return you the distance to that data. And you can do it not for one, but you can do it for, like, let's say I want, I don't know, 10 closest vectors from my data given my input. So that's the way you use it. We're going to be using that later. Right, so another thing that I didn't cover yet is how to actually use it in your project. Again, you're going to get the project that does exactly that, but I feel like it's useful to go over it again. So to install OpenCV on your system, for those of you who don't use the virtual boxes and that they run on Linux on their own systems, you need to run these commands. So the problem is that just lib OpenCV dev, which is already in your system repositories, is not enough, because Sift is actually, so it's not completely free. You have to have a license for it if you want to earn money with it. And that's why it's not part of the OpenCV, which is open. So it's in the separate repository and separate library, non-free. And we're still going to be using it because it's an important concept. And if you ever want to earn money with it, you can implement it on your own. It just took 30 years for a guy to do it, so it's doable. Then what you do is when you install that, you can use the find package command that we've seen already for other libraries. The only thing that we didn't do before is we didn't specify a version. Here, you must specify 2 in order for examples to work. So what you say is, I want to find a package OpenCV version 2, and it's required. Like if it's not going to be found, it will complain, and so on. And then to include the files, you can use OpenCV include dirs, and to use the libraries, you can use the OpenCV libs. So then in your CMake lists.txt, somewhere there's going to be these lines. So you add some library, which is your library, your CPP files, and then you can link your library to OpenCV libs. Okay? And the same goes for programs. So it works for libraries, executables, and so on. Right. So again, like we are going to be using OpenCV version 2. If you install OpenCV version 3, maybe like if you're running the newest Ubuntu, it might be that they distribute the OpenCV 3. Then you probably will need to install it either from source or from some other source of information, because it's hard. Like they changed the interface. A lot of things are broken and different. The functionality is all there, but so especially with using sifts and so on. So the ones who install OpenCV 3 will have to have some more time spent on how to make it all running. So try to install OpenCV 2 if you can, if you must install it. The virtual boxes, they all installed OpenCV 2. The machines in our lab should all run OpenCV 2, so that shouldn't be the issue. This is a link to the example project in case you didn't get the email somewhere either yesterday night or today in the morning. Don't remember when I sent it to you. Yeah, you can go there, clone it, run it. You will see what happens. So I tried to visualize a lot of things. The code should be relatively clear on what happens there. So just use it. Good. So there is two more things that I didn't even cover on the slides. So you can write macros in C++. It means that you can tell a preprocessor to run through your code and just textually replace some parts. I didn't cover it explicitly because it's considered now to be you should use a static function instead or something like that instead of that, so that's why I didn't cover it. But if you want to read about it and how it looks like, if you encounter it somewhere in the code, I feel like it's really well explained on the CPP reference site, so it shouldn't be too complicated to get that. There are also lambda expressions, which we didn't go in this course. I was considering to put it in or not to put it in, and I decided to not bombard you with even more information that we really won't be using here. You can easily code in C++ without using lambda expressions, but if you want to read about them, you can again read about them on CPP reference website. It's again relatively well explained. The idea is that you can always create a function at any point of time, kind of a function in a function, and so on. It's useful if you use it right, not really useful if you use it wrong. Feel free to look at it and decide for yourself if you want to. Okay, and if you want to read about SIFT and how you detect SIFTs in OpenCV, there is a nice article on the OpenCV docs website, so it's linked over there too, so feel free to look at it. And at that, I think that's it for the C++ course. So you're not going to be hearing any more lectures from me on C++. There will be one more lecture that Cyril will give about the project and how it's going to be carried out. I think it's going to happen somewhere in the beginning of the next month, because from next week on, we are at the conference. Either in the end of this month or in the beginning of the next one. We're going to send you an email when we figure out when Cyril has the time and like how it's. So it's going to be definitely either Tuesday or Wednesday. And then the project will be explained to you. You're going to be given some data. But till then, feel free to play around with the project that I gave to you about OpenCV and try to clear up all the questions. I'm not going to be, so on Friday I'm flying away and I'm going to be in Australia, so we're going to have like a gap of 10 hours between us. So I will answer emails, but I'm not going to be in the office. So again, like don't expect my answers to be really quick unless you're writing me somewhere at night. So if you're writing me at night, I'm probably going to be there during the day, so it's going to be a gap of 10 hours. But feel free to still write me emails if you have questions. Okay, so thank you, and we're done for today. Thank you.